Thanks a lot. It's a pleasure to be in proxy of Berkeley. Would have loved to be in Berkeley. So today is I'm going to talk about something which I view as essentially a third revolution in quantum, in basically in the world of quantum. Okay, so let's just start. Okay, so basically, if we look at what happened over the past, God knows, 30 years, well, there was the first revolution 100 years ago of the discovery of quantum. But then the second quantum revolution is the discovery of quantum algorithms. That's basically the revolution in which computer scientists told quantum people, look, there's something here that's interesting, and we may be able to use quantum systems for our advantage. 10 years later came the third quantum revolution, in which basically physicists realized that maybe they can learn something from those quantum computation ideas, not just in terms of what they can do in terms of building computers, but also in terms of understanding something about physics and looking at physics through the computational lens. And that gave birth to the idea of quantum Hamiltonian complexity, to the field of quantum Hamiltonian complexity, and essentially made physicists look at ground states. And I think it was really responsible for the penetration of computational ideas into the way physicists think of their physical systems. I want to argue that in the last 10 years, there has been another revolution, which is led mainly by experimentalists. And while the previous two revolutions were led mainly by theoreticians and physicists were, of course, participating, but it was more coming from the theory community. Here, in the past 10 years, there has been a true revolution coming from the experimental community, in which they actually borrow algorithmic ideas, quantum algorithmic ideas, and completely change the way they think about experiments. Some of those ideas also come from the theory side, but it's mainly coming from, we see sporadic new ideas of computational ingredients like entanglement and error correction and small quantum algorithmic steps, etc., getting into experiments. And I want to argue, first of all, that this is a revolution and that there's theory missing here, meaning that we are behind. There is lots of interesting questions that theoretical questions that are very interesting, and there's of course a lot of interesting experimental questions here. There's actually possibilities of using those ideas to gain exponential advantages in certain quantum measurement tasks and quantum experimental tasks. Okay, so what do I mean? By the way, feel free to ask questions, as many questions as you want. I love questions. Okay, so this is a standard experiment. There's nothing quantum computing about it. It's an X-ray diffraction experiment. One wants to study the structure of a crystal, and there is a crystal sample here. Do you see my mouse? No, right? Okay.
Yes, we do.
You do? Okay.
Mm-hmm.
So there's a crystal sample here, and photons, X-ray photons, scattering off it, hitting a camera, and the camera is augmented with some computer, which allows some post-processing of the locations of where the photon hit, and that allows us to deduce the structure of the crystal sample. Okay, so that's sort of an experiment, a simple experiment, or it's not simple, but it's simple in the sense that it doesn't include any quantum computing elements. Okay, I wanna progress to some examples in which there are quantum computing elements implemented in the experiment, and these are sort of, there's a large variety of them, and if you're familiar with them, maybe a good question to think about is how all these different types of experiments can be put in one model together. Okay, so the first type of experiments comes from sensing and metrology. Example one is the noon states. Noon states are those states that look like noon, n photons in one path and 0 photons in another in some beam splitter, and coherently superimposed with 0 photons in the first path and n photons in another. And it turns out that going from 1 to n, that allows one to increase the precision of measuring some phase that is induced by the beam splitter. Whereas, so if one doesn't use this entangled state and just sends a superposition of a single photon and repeats it many times, that means that one needs to repeat the experiment t times to get only 1/square root of t improvement in the precision. That's the standard quantum limit. But if one does this type of an experiment, then that allows to get to the Heisenberg limit behavior, which is a quadratic improvement using entangled states, highly entangled states, or these entangled states. Okay, so that uses the ingredient of entanglement. Another example is to augment, coming from a different direction, is to augment our sample that we want to say measure with very good precision some kind of frequency that is a parameter of the Hamiltonian. So if we just do it very straightforwardly, then we will have to wait until the oscillations, there are enough oscillations, and eventually we'll get to the standard quantum limit again. And the point is that during that time, the oscillations decay because of noise, and that means that the precision is not enough, and that this is the reason why we'll get to the standard quantum limit. It turns out that if you augment the system by a very small error correcting idea, meaning error correcting small primitive, say 1 or 2 qubits that are very stable, and you use them somehow in a very rudimentary way to perform error correction, that allows the signal to be prolonged, and one reaches the Heisenberg limit in certain cases. So quantum error correction can also be used in very rudimentary ways to avoid the decay of the signal, and therefore gain enough statistics to achieve the Heisenberg limit. Okay, so these are examples from sensing and from metrology. Here's a different example, which comes from the area of black holes, the famous Hayden-Preskill paper, in which one can, this is an experiment, I won't go into the details of it, but of course it's a Gedanken experiment that basically tests the questions related to the information paradox by using entanglement of a large number of qubits emitted from the black hole, and essentially decoding these qubits after collecting them. And that requires a quantum memory and also some kind of a quantum computer. So this is a different experiment that needs a quantum computer if you want to implement it. Okay, so that's another type of experiment. And here's another type of experiment. That's an experiment that its goal is to verify the correctness of a certain evolution of a quantum circuit. So that comes from verification of quantum circuits, and it involves another ingredient which was not exactly involved before, and this is the ingredient of interaction. The ingredient of interaction, coming from theoretical computer science, allows a weak verifier to interact with a quantum computer in a clever way, an adaptive way, one scheme uses an error correcting code, but it's not essential. The point is that we need interaction and we need randomness in order to actually be able to test the correct evolution of the quantum computer. And so the ingredient here is interaction and adaptivity. Okay, maybe I will spend a little more time on the fifth and last example. And that's an example that uses quantum computers to provide an exponentially more precise energy measurement of an energy of an eigenstate of a Hamiltonian, of a certain Hamiltonian. So okay, so this comes from a paper by my student Yossi Atiya and myself, and it goes as follows. So Yossi came with the following idea. Shor's algorithm is the task of Shor's algorithm is to factor a number n described by log n bits in time, which is polynomial in small n, and this is equivalent to finding the order of some number y, which is coprime to n. The order is the minimal r, which satisfies y to the r equals 1 modulo n. And we want to do that in polynomial time, polynomial in small n. And as we all know, Shor's algorithm allows to do that. Yossi's idea was, isn't that essentially equivalent to being able, so there's an exponential speed up here. Isn't that essentially equivalent to being able to perform an energy measurement exponentially fast? So how is that? So Shor's algorithm basically takes this unitary, which takes any x, some binary representation of a number between 1 and n, say, and multiplies it by this y here that we want to find the order of, multiplies y by x modulo n. Now, Shor's algorithm basically creates a superposition over all those elements with u to the t for t varying from 0 to n. So big N is exponential in small n. So the whole point of Shor's algorithm is that one can actually raise u to a power which is exponential very efficiently. Now we can actually look at that as if we have a Hamiltonian, H, which is this unitary u plus u dagger, and look at e to the I ht, where t is very large. And it turns out that by the same idea that one can actually take u to an exponential power, this is very special, the fact that we can take u to an exponential power. If we don't have a structure, we need to actually multiply u. So e to the I ht is something that we can actually do here efficiently. And this is something that can be applied by a quantum computer because of the special structure of u in time, which is polynomial in n, for t's which are exponential in n. And so one can view this as the ability to fast forward the Hamiltonian, to take a quantum computer and simulate e to the I ht for a certain amount of time t, but the simulation on the quantum computer takes only logarithmic time in t, or polylog. And it turns out that this remarkable ability allows us to perform an energy measurement for an eigenstate of h exponentially with exponential precision, very efficiently. So how does this go? Well, if you're given this initial state psi, and you add this state here, 0 plus 1, and conditioned on 1, you apply e to the I ht, then you have, since psi is an eigenstate and h here becomes an eigenvalue, you have this qubit in a state which has information about the eigenvalue of the Hamiltonian. And if you can prepare polynomially many qubits like that, with t which can go up to exponential, you can, this is very well known, you can actually derive exponential precision for the energy. And it is, and what we proved there is that fast forwarding, this ability to apply e to the iht in very efficiently in time, which is much, much shorter than the actual time, by a quantum computer. This is the same as the ability to measure the energy exponentially, with exponential precision in time, meaning in computational time, which only grows polynomially with small n. And so this is a violation of the so-called time energy uncertainty principle. It's an exponential violation of this, because delta E, the precision here, is exponentially small, and delta T is just polynomial. So, okay, so these are sort of some examples where surprising or interesting advantages can be actually achieved using ideas or methods coming from quantum computation. And there, it seems like a very, I mean, the variety of these things is quite vast, and one can actually ask, well, what puts everything here in some common framework? Why am I talking about them together, and what makes
Dorit,
them?
can I ask you a question?
Sure. Oh, hi, Zeph.
Hi. So there's special, this thing that you just described is for special kinds of unitaries, right? That you can do this for. Can you characterize what those are? If I got that right, maybe I didn't get that right.
In fact, you can do it for any t. But let me not get into this. I mean, even if you don't have, you can do it even for specialties, and that's enough. But let me not get into this, because
Sure.
This is a detail. Okay, so one can look at all at those examples and ask, well, then why do I put them together? And if all of those are related to some physical experiments, we're trying to measure something.
So do you mind if I ask a quick question about previous slide?
Yes.
So this sounds remarkable, but at the same time, I'm a little bit wondering whether this is a fair argument, because here you're assuming you can prepare psi, which is an eigenstate of the Hamiltonian whose parameter you want to estimate of. However, the fact that you can prepare exact this has to be exact eigenstate. It cannot be an approximate, because otherwise your energy resolution, if it's a linear combination of multiple energy eigenstates, you won't be able to resolve this energy because they are in superpositions. The fact that you can prepare the state within the energy resolution better than something means you already solved the problem. You already know the value in some sense, right?
So there are two things I should have made more clear. First of all, the psi is my input to the problem. I'm not preparing it and then measuring it, but I'm assuming that somebody prepared for me psi, or I have some state in a physical system, and I just want to estimate its energy. Now, this is a very good point, and indeed, physicists that hear about the ability to measure the energy with exponential precision, or to measure something with exponential precision, raise their eyebrows, because we cannot hope to prepare or to have a state with exponential precision. But this exponential precision, there are two different types of exponential precision. Even if the state itself is, say, contaminated a little bit by another state, which has a slightly a different eigenvalue, so you'll have the superposition. The effect on the algorithm is that you'll have the correct answer with very good probability, with exponentially good probability, and you'll have another answer with just a small error probability. It doesn't affect the precision. It just affects the probability that you get the correct answer. But the correct answer will be given with exponential precision. So you will get the correct answer with some very good probability, And the precision of the answer is to within exponential error.
Can I ask a quick question?
Sure.
Dorit, so how different is it from phase estimation? I mean the task seems exactly like phase estimation, but you seem to present it differently.
I should have said phase estimation. It's phase estimation. There's nothing, there's no, technically, there's nothing.
Okay.
Just a phase estimation.
You found something new.
No. This is
Okay.
not, this is just a point of view on phase estimation, which allows this, of course, yeah, sure. I should have said the word.
Okay, no, all fine.
But the point here is that is this ability to do fast forwarding that implies this exponential relation for every Hamiltonian. Okay, so that works for other Hamiltonians as well. But this is basically essentially it's a mapping of phase estimation to the notion of energy measurements.
It need not actually.
It's a Shor's algorithm to the notion of energy measurements. Hi,
Dorit. It need not actually involve phase estimation. I think their main point is that when you have structure to the Hamiltonian, like in this case, you can do modular multiplication, modular exponentiation, then you can fast forward. So for example, the harmonic oscillator for which we have the basis functions, you could also fast forward and get the energy eigenstates just as easily.
Right. So yeah. So for example, every commuting local Hamiltonian can also work this.
That's right.
In the same way.
Right. I think it's a beautiful interpretation.
So okay. So now we can look at all these experiments, at all these suggestions for experiments, and we can ask, well, then, what is a physical experiment? If all those are experiments, how do we characterize a physical experiment? How do we model it? So how to model the most general quantum experiment in a way which is useful for us. So we want a model that will enable us to study the measurement processes and compare the resources and understand how precise they can be with those amounts of resources. And we want that to not depend too strongly on the physical implementation, just like when we ask about the complexity of a quantum algorithm, we don't want that to depend too strongly on the implementation. We want the separation. So we want to think of measurements as protocols with computation complexity associated with them. And we want to study those experimental protocols from a computational point of view. So we want to sort of walk in this field with the help of an experimental version of the extended Church-Turing, the quantum Church-Turing thesis. By the way, I'm not sure. I see here only experts in front on my screen, but if I say something that's not understood, please do ask questions. My screen only shows me just a few friends. Okay, so we're looking for such a model, and I want to basically start by writing up a first attempt to come up with a model, a general model for a quantum experiment. So what would that model be? What is a quantum experiment in its most generality? So I think that the most general thing that one can say is, first of all, we are looking for some kind of protocol that will allow us to compute a function given access to some physical system. We want to be able to take this physical system, and so this is the physical system here, and we want to map it to some number, or to maybe a probability distribution over some numbers. Okay, so maybe some string, or maybe some probability distribution over such strings. And this is a physical thing. Okay, so this is physics. This is a physical system. And maybe the first attempt to write down such a model would be something like that. I showed you an example in which the system is the protocol is interactive. So and we know that we don't understand the physical system, so maybe we should treat it as a black box. So maybe the first attempt would be something like there are qubits that can be used, and this is time. And we query here our black box physical system, and then we maybe perform some quantum computation, and then we query it again, and so on, so forth, and then the output will be the output of this function. We measure, and that's the output. So it's sort of a black box model. I wish I could do raise of hands if you think this is a good model, but I want to argue this is not a good enough model. And the reason I want to say this is not a good enough model is, let's look at our first example of an experiment. By the way, this is together with Jordan Kotler and Shailiang Shi, we looked at this question, and this is the model that we came up with. We call it QAMs, quantum algorithmic measurements. So let's look again at this example. So we have this crystal sample, we have X-ray photons, we have the camera. One very important ingredient here is that indeed the experiment computes some function from the physical system to some classical output, but we're not given full access to the input being the physical system. We're not given full access. Of course, we're not given a full description of it, but we're not even given full access to it, meaning we can't actually interact with all its degrees of freedom. Some degrees of freedom are hidden. The degrees of freedom that those who operate the camera and the computer, etc., can interact with are only the photons. So basically, there's not just two things here: the space, the physical space, and the workspace in the experimental lab, but also another Hilbert space, which is hidden, that contains all the hidden degrees of freedom. And there's a very important ingredient, which is the interaction with this hidden set of degrees of freedom is done via the photons in this case, but via some message between the degrees of freedom and the workspace. And so this brings us to the following model. It's a simple combination. We want it to be simple. Well, I'll show it in a second, but let me first say that we will have three subspaces, three subsystems. The workspace that we have full control over, the nature space, on which we don't have any control over. These are the hidden degrees of freedom, and the photons which allow us to interact with nature. And you should think of nature as something that remembers that everything that needs to be remembered about the physical system. What is its? How does it behave? The state that evolves between different times of interaction with the workspace or whatever. Okay, so we have these three spaces, subsystems, and the definition of quantum algorithmic measurements will be as follows. It's a hybrid of quantum interactive protocols and those black box algorithms that we started from. So here we have these three registers: nature, lab, and workspace. And we basically have an interactive protocol, meaning a quantum circuit, something that has to do with a quantum system. It's a super operator, we'll denote it by epsilon NL, another quantum circuit, epsilon L, etc. And the physical system will be described by two things. This is my input. I have access to it only in a limited way through the lab register, but the physical system is described by two things. One is the state, the initial state, rho n, and the other is some super operator epsilon NL. And this is all this is the entire description of the physical system. And this rho n allows for remembering the state and whatever you need to whatever the physics needs to remember about itself. And the workspace has both interactions with this nature, and it calls this lab oracle super operator as a black box. Now, okay, so this is a familiar thing that combines these two notions, a hybrid of interactive protocols and black box algorithms, these two familiar notions. And I want to just say that there are two.
Sorry, Dorit, I'm a little confused about what is what here. So your workspace is who's the workspace, and what's the? Can you say the role of these three again? Which is which in the?
Sure. So this is nature.
Nature meaning things outside of your lab or outside of your actual apparatus, or is it the environment?
Nature you should think of as the crystal. So it's a physical system that contains, but some of its degrees of freedom of the physical system are accessible and some are not. Nature are all those that are not.
Okay, so is it the environment of your so if you had some apparatus in your lab, is it the environment? Is it
No, I don't think of this as the environment. So I think the crystal example is a good example. I want to actually understand the structure of the crystal. And so the crystal degrees of freedom are n. Okay, so this is actually what's describing for me the physics that I want to understand, but it's hidden for me. And L is my way of interacting with it. So L, the lab, is basically in my example, these are the photons. Okay, and W corresponds to the camera and to the computer and to everything that I have in my lab that I have full control over.
Sorry, Dorit, I'm a little confused about something, which is, so what sort of description do you have on N? Do you know how big it is? Anything of this nature? Nothing.
No, I don't have any control over it. I'm viewing, I'll define it in a moment more precisely, but basically, let me just show you and then I'll go back to this slide, okay? It's not written, I meant to write it. Okay, so I'll write it here. So basically, there are three ingredients in the model. The first is what we call the lab oracle. The lab oracle is basically what describes the physical system that we want to study. And the lab oracle is just a pair of two things. So lab oracle is a pair of two things. It's rho n, the input state, and epsilon nl. And this is a superoperator, this is a state, and I don't know it. Both, I don't know the lab oracle. I may have a guess, for example, I may have an assumption that the lab oracle that I can interact with belongs to some set. May have a promise like that. But other than that, I don't know what it is. And what I want to do is I want to compute a function of this lab oracle.
Maybe the question I was confused about is you are sort of assuming that this nature follows quantum mechanics. That much you have to assume. Otherwise,
yes. I'm not. Yeah, I'm not playing here the game of not believing quantum mechanics or anything.
Okay.
I'm playing here a game. I mean, you could embed, you could implement, you could present in this scheme an experiment that tests, for example, whether a system follows a quantum circuit description. But the description of tensor products of Hilbert spaces, that I believe. Okay. This is, yeah. Okay.
But are you actually assuming that nature follows quantum mechanics, or only the way you couple to nature follows quantum mechanics? Because I don't see anything specific quantum mechanical in the, I guess it could be as complicated as you want, right? The rho n part. I mean, there's no notion of locality, for instance, right? So there's no reason to obey the tensor product structure, really, I guess. Unless you put constraints on how the E acts on the n system.
It's possible that one can actually release the assumptions on quantum mechanics here in the hidden degrees of freedom. Here we are assuming, I mean, we're saying there's quantum circuit. So I haven't actually thought about what happens in this way. We are actually assuming that physics is described by quantum mechanics to the extent that it's described by Hilbert spaces, and the description is quantum mechanical. And we just want to basically extend the quantum algorithmic picture into quantum experimental protocols within quantum mechanics. So it's
for instance, you could be radical and completely freeze the way you couple to the environment if you make it just as big as you want, and just use the environment rho n to program the E, right? So
I suggest, I mean, I think this is a very interesting question. We should discuss this in the discussion.
Yes, okay.
Okay, but for now, let's assume quantum mechanics. I'm just, I'm basically thinking of this as if it's an extension of the question, what kind of algorithms are there on quantum computers? Now I'm asking, what kind of experimental protocols are there in the world in which everything is described by quantum evolution? Okay, so what we're claiming is that this model seems to be universal. I'll describe this in a moment, but there are three ingredients to this model. First of all, this is the lab oracle, the initial state, and the superoperator. Then there is then there is the task. What's the task? Let's move to the next page. So the lab oracle here is this rho n epsilon nl, this pair. Okay, now the task, well, basically task is sort of the problem that the experimentalist faces. Okay, so the experimentalist wants, for example, to describe the structure of the crystal in some classical way, which is, I don't know, which is comprehensible. So what she wants is she wants to compute a function from the set of lab oracles that are possible. So she's assuming something about the crystal or something, I don't know, that is described by a local Hamiltonian, or there's some description, there's some assumptions. Plus, she might also be getting some description of what kind of experiments she wants to perform. For example, at what temperature she wants to estimate something about the crystal, or things like that. So these there's an extra parameter, classical parameter, that could be given, which could be specification of the experiment. So the function takes this extra parameter and the set of lab oracles, say, I don't know, let's put here n, and outputs some classical output. Now, this classical output is extremely general. Okay, it could be, for example, the output of machine learning, quantum machine learning algorithm that looks at a physical system and outputs a classical description of a quantum circuit that learned how to predict the behavior of that quantum system. It's very, very general. Okay, and in fact, it's not exactly the right thing to do to put here deterministic function. The right thing to do, given the fact that the lab oracle could come from a continuous set, is to be able to output some probability distribution. For every lab oracle, it can output a probability distribution. I'll just say very quickly why. It's not a very important point, but why? Because for example, think of a tomography situation where the lab oracle could be something that generates a state, and you want to understand what's the state, you want to do tomography to within some approximation. Now, for this to make sense, you cannot request that on a continuous space, there is a function that's defined, and and you want a protocol that computes this function correctly to within a good probability for every point, because there will be points in which they're extremely close, but the function will be defined differently on two very close points, arbitrarily close. So if you want to make functions which make sense from a smooth set, you want this to be actually probability distribution, but never mind. Think of deterministic for now. Okay, so that's the task, and the specification of the task is not only the function, but it also, the experimentalist is facing also the problem that she has some limitations in her lab. For example, that the gates that she has are limited, or that there is limited interaction between the workspace and the lab register, etc. So there's also some kind of a set of gates that is allowed with the restrictions on that set of gates. For example, maybe that on W, she's only allowed to apply classical gates or something like that. Okay?
So Dorit, I didn't completely follow what you said. Could you say it a little faster so I can?
Sure. Okay. So, but which one didn't you not follow? The task
the entire task? Yes. So what?
Okay. So but the lab oracle is fine, right?
Yes. Yeah.
The lab oracle is fine?
I think so.
Okay, so there is a physical system, that's the lab oracle, and the task is basically the task of, is the problem that the experimentalist faces. She wants, for example, to design an experiment that will take her sample, her physical sample, and will output some classical property of it. And she has some specifications of what she can do in the lab. That's G. That's the set of gates she can implement. The task is her specification of the problem. Was that fast enough?
Well, I guess, and is the specification in terms of nature? So that's what's puzzling me. So does it say what function of nature you want to compute? In which case, it's a pretty hard thing to say. So how do you specify all that?
I'll give an example in a moment, but for example, you can say that that you have two samples, that your sample is taken out of two possibilities, and you just want to know which one it is. For example, you have a system which is either 2 local or 3 local, and you just want to know if it's that or that. Okay, so you can assume something about the lab oracles, that they come from a subset, say local Hamiltonians, and you want to find out their locality, for example. So you don't have to actually, okay, is that good? What's the QAM? The QAM is actually the solution, the experimental protocol that the experimentalist actually runs in her lab, meaning the exact specification of how to implement, how to put the beam splitters here and the magnetic fields there, etc. But we are viewing it as a quantum circuit. So we just describe this quantum circuit, meaning these quantum circuits in the middle, plus the application of a query. So here we don't know epsilon and L, but the experimentalist just says, okay, at this point in time, we apply epsilon and L, and she can make a query to that epsilon and L. That's the QAM, a specification of this protocol. Is that clear? Yeah? Okay. Okay, so that's so this is the model. How are we doing on time? We're very, very slow here. Okay. So this is a QAM, and if you run through our examples, which I will not do, you will see that so I did actually say a little bit about how you model the X-ray diffraction, where here this is the crystal, these are the photons, and this is the workspace. But for example, the measurement with a quantum error correcting code, well, it's just exactly this. The sample is here, And the lab here is just extra qubit or two, which can be much more robust, and you control it. And the quantum circuit is essentially this rudimentary quantum error correction that you apply all the time. And at the end, you measure. So, okay, so verification is more complicated to explain, and I won't go into that. And there were other experiments, but it's a very good exercise to try to think about any experiment that you want and try to put it here. And I think that you will see that there's no way around. So for example, in verification, maybe I will say one word about it. In verification, you want to test that the certain system is actually behaving like a quantum computer. What's a quantum computer? It's a hybrid, quantum classical hybrid, which takes descriptions of quantum gates, classical descriptions, and applies it. And you want to test that it does things correctly. So you cannot actually go into exactly what it does. This is the hidden degrees of freedom, but you can give it various instructions and test it. So this is, I was trying to convince you why you need hidden degrees of freedom in the model. You cannot just apply black box. Okay, so let me very quickly say just a little bit about what are some results, and I want to move to the discussion, which I really want to hear what people have to say. Okay, so just naturally, quantum complexity is measured by number of gates and by the oracle calls. So it's really trying to quantify what is the complexity of an experiment. And we believe, as I said, that this is a universal model for quantum experiments. And one can ask now, how much do the new computational ingredients that quantum computation brings along, how much can it give to quantum experimentalists? Maybe we can design new quantum experiments using quantum algorithms here and using adaptiveness and using various things. And there are sort of many different questions to ask here. Trying to separate the types of experiments and what kind of experiments actually can buy you advantage. So you can ask whether coherence between the workspace and the lab register buys you anything, or maybe the type of experiments that are done usually in the lab, in which you just let the system just evolve and then measure it and then collect information and just do classical post-processing. Maybe that is good enough. How does adaptivity get into the picture? Is this useful at all or not? How do things behave in terms of the number of queries? Maybe you don't need too many queries. And how complex do we need to make those quantum states that we prepare here, and the quantum operations, or maybe very simple ones are sufficient? Okay, so I want to tell you one result that we have, and also about some other results that are very related, and end by that. And basically in our paper we concentrated on the following question. We wanted to really ask, how much does coherence in time and in space bias? And what do I mean by coherence in time and in space? I mean, let me jump because we are in lack of time. So we wanted to study what's the difference between this coherent model that I told you about and the incoherent QAM, which essentially can describe most experiments done today, in which between every application of the physical superoperator, there is some complete measurement being applied. And the interaction between the workspace and this physical system is classical. But other than that, you can prepare complicated states and you can apply complicated measurements, etc. And we wanted to know, does it bias a lot or not, the coherence? And it turns out that it does, that we found two tasks which are physically motivated, or at least they're toy examples, toy versions of physically motivated tasks, in which there's exponential advantage to coherent QAMs. We need coherence both in space and in time.
Sorry, Dorit, can you clarify? I don't know what, maybe it's a dumb question, but I don't know what coherence in space or time means.
So I tried to define incoherent by basically saying that the interaction between W and L is by LOCC, it's classical interaction, and that there is complete measurement between every two applications of the lab oracle superoperator. So this complete measurement prevents coherence in time, and the fact that we require LOCC here prevents coherence in space. So this is incoherent, and anything else is coherent.
Okay, even though it might be partially coherent or something like that. We
Yes,
don't care.
yes.
We just, okay.
Yeah,
okay.
yeah.
Okay.
We want to separate incoherent from anything that's not incoherent, that
Thanks.
uses coherence to some extent.
Great.
Okay.
Thanks.
And what we showed is that for two problems, there is an exponential advantage. The first problem is the following. We want to distinguish between the following two lab oracles. One is the system picks a fixed unitary, high randomly, and commits to it forever. Here is a picturesque way of looking at the lab oracle description. The other lab oracle is it picks a new unitary every time. And clearly, if you can apply a swap test, you just apply twice this unitary, and if it's the same, you can test that it's the same. So a swap test would do by two applications. And the question is, can you do it incoherently? The other problem is, so the first problem has to do with, can be associated with the question of checking whether a Hamiltonian is periodic or is time independent or not. The other problem is maybe more physically motivated, is checking the symmetry of different systems, whether their evolution is unitary or orthogonal or coming from a symplectic form. And this too turns out that one can actually come up with some not too complicated swap test thing that basically distinguishes between these three symmetries. What we managed to do is and this is a complicated proof, which I won't say anything about, we managed to actually prove a lower bound for the case of incoherence. It uses Weingarten functions, if you know what that is, and the thing that makes it hard is the adaptivity. The lower bound works also for adaptive case, and that makes the integrals. You need to do something to make it work. Okay, so what we get is that efficient coherent quams versus incoherent quams that need exponentially many queries. And so there's an exponential advantage for coherent over incoherent experiments. Now, one can wonder whether well, aren't there other, don't we already know that from quantum algorithms that coherence helps? For example, Simon's algorithm requires coherence. Isn't that sort of a demonstration of such an advantage, at least maybe not experimentally, or maybe not of interest to experimentalists, but at least something? Well, no, because Simon's advantage actually in this model of incoherence, it's actually incoherent, because you can prepare a superposition, which is a product state, and you apply the oracle, and then you measure in the Hadamard basis, and that's it. You don't need any coherence. So it lies in the incoherent model. It even lies lower in the hierarchy. It's just local.
Dorit, is it clear that these two different mechanisms of getting a quantum advantage are distinct? I mean, there's also some mechanism behind Simon's algorithm, right? So is it clear that it's really a distinct mechanism, or is it just that it appears distinct? Maybe
you'll have to define what do you mean by mechanism. I want to distinguish it okay, let me say one more sentence, and then maybe it will say something, it will answer. Interestingly, after we've just found that there are examples, there are known examples that were just recently found that basically provide lower bounds on depth algorithms, of quantum algorithms. So this particular result by Chia, Chang, and Lai, they defined an extension of Simon's problem in a recursive way, in which you cannot actually find the value of the function without asking the oracle many times coherently. And they showed a depth lower bound, but this can be massaged to a lower bound also on the quantum complexity. And this is another depth lower bound for the welded tree algorithm, quantum algorithm. So
I guess my question would be a bit like, do you need coherence for quantum speedup? And Simon's algorithm seems to suggest no. So my question is, like, in that case, what does give the advantage there as compared to coherence?
So coherence is not something that lies in empty space. Here, coherence means coherence between. I mean, this has a context. The context is that we're talking here about a new type of exponential advantage of quantum computation because of the motivation. It's a new type because we're talking about experiments. And for experiments, it's the same old entanglement. It's the same quantum states that we all know, but the application is very different. It's these are, and the way you look at things is different. So what we get here is an exponential advantage for the application of quantum experiments, where the setting is this interaction between lab register and work register, etc. But the type of, the mathematics is the same. You have entanglement and you have
Okay, but the difference is that kind of the oracle has a memory, right? Which in Simon's case, it just doesn't have. So there's not much of a point in some sense to talk about that there. Right? I mean, it's essential for your example that at least one of the cases you want to distinguish has a memory, right? So it remembers the random unitary.
Right, and this is what, here the depth is achieved not necessarily with a memory, with an extra memory, the depth lower bound, but it does require the coherence in time between the different oracle applications.
Actually, Dorit, would you get such a separation from every quantum communication complexity speedup? So if you have an exponential speedup in quantum communication complexity, would it automatically give you such an advantage?
No, because quantum communication complexity actually cannot give you any advantage in quantum complexity, because the exponential separations are between log n and n, right? Once you talk about the size of the input, so in communication complexity, you can only hope to have separation between log the size of the input and the size of the input. That's the exponential separation.
But if you have an oracle, can't you get more? Okay, well, we can take it offline. Yeah. Yes.
Okay, I looked at it a while back. I don't have an answer right now, but I think not. Okay, so
can I follow up on Mesh's question? Maybe this is brief. Maybe there is a class where you can show you have a similar set of separations, which would be the quantum channel discrimination problem when you use entanglement versus no entanglement, because there, when you serialize the entangled query of the quantum channel and you want to distinguish classes of quantum channels, so it's a decision problem again, the serialization would correspond to your coherence in time.
Let's take it offline. It's let's discuss this. It's I need to think a little bit about it. But let me just I forgot to mention here, the setting that we're talking here is very close to a setting that Huang, King, and Preskill also discussed in the context of quantum machine learning. And they found a quantum exponential separation between coherent and incoherent, different definition of a problem in the context of this quantum machine learning, but not in their case, the experiment, the quantum experiment, is not efficient, so it's just in query complexity. But they also were interested in very similar questions, and the setting is very similar. Okay, so to wrap up just with the questions, are basically, I think we are at the midst of a new era of quantum experiments and quantum measurements being slowly, or maybe very fast, incorporating more and more ingredients from quantum computation into them. And there's lots of theory that is missing. Like we don't have good algorithms, and I'm sure that there are fancy quantum experiments that can be done in which maybe one can use sophisticated states and highly adaptive, structured adaptive experiments that are not being used now. So this is my first question. And the second question, which I didn't get to talk about at all, is this, all this gets completely, how do you say that? Nothing is correct when there's noise. The swap test, for example, between n qubit states, when there's noise with some probability per qubit, the swap test doesn't work. There's noise with some constant probability. The swap test fails for both situations of orthogonal or similar states. So can we actually talk about such advantages in the quantum complexity setting, even in the NISQ era? Okay, so thanks. And I'm very happy for questions.
Thanks, Dorit. That was very interesting. So questions is...
Yeah, there were two questions that we didn't get to during the talk. So there's one from Alec Darmus, and is how does the qual model of experiments apply to natural experiments, situations where the experimenter cannot control the means of interrogating rho n, which she can only observe? Gives examples of jumping up on scale using gravitational lensing to try to characterize BHs.
Sorry, I need some explanation of about the question.
Yeah.
Can you interpret the question?
I think the idea is about if you aren't able to control the interrogation, then what happens in this qual model?
But I mean, the whole idea is that I model in the qual model, what is it that I'm able to do and what is it that I'm not. So I have some control, and that is sort of put in this part of the picture. This is what I do control, and this is what I don't control. And so if I don't control anything, then that's a problem. But for any such setting, there will be some quantum complexity of the problem. It could be that if you don't have enough control, you can't do anything.
Alec, did you want to ask more?
Yeah, maybe verbally. I guess in my putative natural experiments, the choice is really just to choose the black hole in terms of what galaxies might happen to be behind. So the notion of natural experiment, astronomers are stuck with this approach. Yet nonetheless, they're observing phenomena that have quantum aspects. So it's just a question about the boundaries of the qualm approach.
Yeah, this is, so basically you're saying this Gedanken experiment of Preskill and Hayden, this is, it's very nice, but this is too Gedanken. You can't actually interact with a black hole. So basically it's just observing some properties and post-processing.
Exactly right. You choose your black hole and I don't know, hope for the variation in interaction that's appropriate.
If John is in the audience, maybe he can actually contribute here more than me. I don't know if he is, but I think that once you don't have interaction, then the setting is less interesting. You don't have, there's no notion of entanglement between the system and your experimental device.
Yeah, okay, I'll buy that. Okay.
Can I ask you a question? So
Sure.
I'm trying to still set my mindset for this new setting. So is it different from having a quantum computer that I have a full access to, which is coupled to the environment, which has memory? So how is it different from that setting? Like so I'm just calling it environment for your nature, except that now this environment has a memory. So like, how is it different? Like, is it the same situation?
Well, that was Umesh's question from the beginning, that why don't I just refer to this as the environment? But the whole point is that these hidden degrees of freedom are degrees of freedom that we are interested in.
So this, your interest is in the environment, therefore we don't call it environment. I see.
I mean, you could I mean, I don't know what you mean by environment, but sometimes you could actually treat the environment as a physical system and ask some question about it.
I see. Thank you. Yeah.
But I think it's not completely meaningful to separate between rho and between E, right? Because there's inequivalent representations where you shift complexity between the two of them.
Yeah, it's
not. I think the most radical interpretation would be that you have a fully programmable quantum processor in the E, and then you encode the whole process in rho, for instance. Then you can get any E you want from this rho, right? So you could have a hardwired E if you would have an infinite system. And this tells you that you can shift quite a lot of complexity between the two.
Right, but you don't care about the complexity of both.
Right.
I mean,
I guess it depends. The same is true for physical theories, right? I could say I do X-ray diffraction, and my description of my crystal is not a crystal; it's full quantum theory, and then the state is actually saying there are atoms sitting in these positions, right? That's probably not what you would usually do, but that's one option. Mm-hmm. So I think there's also in the normal modeling of a physical situation, there's flexibility, what you assume as your state and what as kind of the interaction. Mm-hmm. But probably one is more natural in a given situation.
Yeah.
It occurs to me that maybe what's confusing Umesh, or what I got stuck with in the beginning, is could be alleviated by thinking of L not as the lab, but rather maybe the laser. So for me, like N was an atom and L is a laser. And so Norbert's point is a little more difficult in this case because the laser can only do certain things to the atoms. And so anyway, Dorit, I very much like your framework, and I think it can describe everything that I can think of in terms of these kinds of experiments.
Okay, but laser is a good way to make an excuse for the L.
So would you agree with that, Dorit? But wouldn't that limit your experiments if it was just a laser?
No, I think that laser is a proxy for basically everything that allows an interaction between me and what I don't have access to. So I was joking. It's not really enough. It's basically, for example, in the verification protocol, what you need here for L is to be able to contain your few qubits that allow you to interact with the physical quantum computer, as well as some polynomially many classical bits that basically provide you with a description, with the ability to provide a description to the quantum computer. So you need an elaborate, sufficient freedom in this L.
So in particular, in general, you might even have n entangled qubits, which are part of this interaction.
Definitely, yeah. And
But an experimentalist would just call that a laser still. It's just a very sophisticated laser, maybe a single atom laser, which happens to be controlled by a number of qubits. So its light from query to query can be highly entangled with the previous query.
Yeah, it's a question of It's a question, maybe, I mean, I don't know if it's possible to actually reduce the whole framework to something with only one qubit here. For example, that would, it could actually need, it could be that for the general framework, you actually need many qubits to interact at the same time, and you can spread it over time. I don't know.
That's good, but I would be happy to let you have multiple lasers.
Yeah, okay.
Related question, then is it different from the following? So you have a quantum computer and you have a system of interest that undergoes its own quantum channel. And there's a type of coupling between the system and your quantum computer that you can turn on and off. And there are many different types of couplings, and you can turn each of them like individually on and off each time you do. So can you model in this way? Is it the same?
And the coupling is between a quantum computer and your physical system, and you just change the coupling?
Yeah, and then the coupling has a specific form, could be time dependent, but constrained somewhat.
Well, it depends on what constraint you have, because this quantum circuit in general is a general quantum circuit. So if the coupling can allow for general interactions, then...
So I do have a quantum computer, so that's the general quantum circuit, but some component of the quantum computer is coupled to the system of interest with a specific coupling that I can only turn on and off.
I think the answer is yes, right? Because that's the epsilon and L.
So is this specific coupling that you can turn on and off part of the thing that you're trying to study? Or is this what you are trying, your probe that you're trying to use in order to measure?
Yeah, between the two, like between the object we want to study and the object that I have access to.
Okay,
Interface.
so for me this is part of your quantum circuit, and it may not be sufficiently expressive to actually just limit the coupling in a very specific way. If the coupling is general, then of course it's this model.
Okay. So what do you say to moving the rest of the discussion to GatherTown? I put a link in the chat and the Q&A, so please take a look and is that okay, Dorit? Should we
Yeah, let's do that.
Okay, great. Well, thanks again, Dorit. That was fantastic, and let's continue.
Thank you. How do I move there?
There's a link in the chat. You should have it anyway, but I just posted the link in the chat. Okay, Ashley posted it again, so it's the last entry in the chat. Okay.
Thank you.
Okay, great. See you all there.
Bye-bye.
Bye.